Yeah, love. So today we're gonna solve problem combination sum. And I'm turning off. No, I got a sensor here. First of all.
Line 75 list, the link will be in the description. So we are doing one more problem and have very few problems from this list remaining. So we're given an array of distinct integers called candidates, and we're given a target integer called target, and we just want to return a list of all the unique combinations of candidates where all those numbers end up summing to the target value. And we're allowed to return those combinations in any order, and we're also allowed to use the same number from candidates multiple times, but we don't want to have duplicate combinations. For example, if 2, 2, 3 sums up to 7, right? That means 3, 2, 2. These are the exact same values, right? Just in a different order. These sum to 7 as well, so we don't want to add both of these combinations to the result because they're the exact same. So what we're saying is we want combinations, we don't want permutations that end up summing to the target value. So in this example, you can see that we are given these candidates and a target of 7, and we have two different ways that we can sum up to 7. Of course, 7 by itself does sum up to the target, and two occurrences of the 2 value and one occurrence of the 3 value added together are going to lead to 7 as well. So then we return these two combinations as our result. So I would say the difficult part about this problem is trying to figure out how to eliminate duplicate combinations, right? For example, if we just brute force it like a decision tree, so we have 4 different values we can choose each of them an unlimited number of times. What we can do is have 4 decisions in our decision tree, right? Like that might be the naive thing that you start with. So we would get 2, 3, 6, and 7, and then we'd basically continue that, right? On one path over here, we would find, okay, we found the 7, so we found the target, right? So we found one way that we can reach the target. So therefore, we don't need to continue down here because as we add more numbers, all of these values are going to be positive. So as we add more numbers, we're only going to get a sum larger than the target. So, I think it's kind of obvious why we don't continue down this path, right? But down here from the 6, let's try to continue, right? We can add a 2, so we'd get 6, 2. We could add a 3, so we get a 6, 3. We could add another 6, so we get 6, 6. And we could add a 7 where we get 6, 7. So notice how all of these are going to sum to a value greater than the target. So down this path, we never ended up reaching the target. We only went over the target. So we don't continue down any of these paths, right? But now let's continue down this path. So here we can get another 2. We can get a 3. We could get a 2, 6, but in that case we would get 8, which goes over our target. We could also get a 7, 2, 7, but that also goes over our target. Now here's the part where we're going to end up getting duplicates. So I'm going to show you why this type of decision tree does not work. So here we could get a 3, for example, right? So we get 2, 2, 3. Now that 2. Notice how both order we obtain one combination, but does not have the. We know that we have all combinations that include this 2 value, right? And see if any of those combinations leads us to the target value 7. Now we could also. So then, if we make a second decision over here, right? This decision we're definitely including at least 1, 2. Now, if we go down this path, we want to make sure that none of the combinations down
Used to.
this path ever match the combinations down this path. How can we guarantee that? Well, in this side, we said we're definitely including at least 1, 2. How about in this side,
No
we
sound.
don't include even a single 2? So basically, we skip 2. So here we're going to have an empty array because we skipped the 2, right? All we said is we were able to start from here, but we said no, we're just not including a 2. We're just going to do combinations with these 3 values. That's going to guarantee that none of the combinations on both sides are going to be matching. And that's basically the logic that we're going to follow. So from here, remember, we can include multiple 2's if we want to, right? So one decision here could be including a second 2. So we get 2, Now, this path is going to include all combinations that include at least two twos, right? But remember, our definition for this decision tree needs to be recursive, right? Because we don't want any of the combinations down this path to be the same as any of the combinations down this path. So what we said here is we're going to include two twos. How about down this path? We say that we're not including any more twos now. What we're saying is we had one two, but now we're done. We're skipping twos. Now we're only going to use values from here. So that's the recursive thing, right? We're basically doing the same decision down here as we did up here. So here we're going to say we ended up skipping the two, and we still only have one single two. And so let's just continue to repeat that. So over here, we're going to add another two. So we'll have two, two, two. And over here, we'll say, okay, now we're done with twos, right? Where we're going to keep ourselves at a limit of two occurrences of two. And we're basically going to continue this logic until we get to our base case. So over here, you're going to see if we ended up having four twos, we'll get a target of 8. So therefore, we went over our target value, so we're going to stop. But down here, right, this was our path where we said, okay, we're not going to include any more twos in this path. So here we can make a decision. We can add a 3, so then we get 2, 2, 3. So we're continuing that recursive definition. And so notice how we have 2, 2, 3, that's 7, so we did find at least one combination. But remember down now, if we make our decision to the right, we want to make sure we don't have any duplicates from here. So on this side, we decided to add 1, 3. How about down this path, we say we're done adding 3s. We're not even going to add a single extra 3. So this is going to remain as 2, 2. Now, I think it's pretty obvious that down here, since we're only allowed to add values 6 and 7, neither of these is going to end up leading to the target. If we add a 6, we'll get a total of 10. If we add a 7, we'll get a total of 11. Neither of these, both of these go over our target. So let's quickly run through the rest of the decision tree. So over here we said we added a second 2. So over here, we're not going to be adding any more 2s. So here we're going to add a 3. So we get 2, 3. And over here, we would skip adding 3s, right? So we're not going to add any more 3s. This is going to remain as 2. Now down this path, at this point, we have a total of 5. So we're only allowed to add values 3, 6, or 7. All of those are going to end up leading to a total of greater than 7. So we won't be able to find any solutions down this path. I'm just skipping and drawing it out because we're kind of running out of room. Now over here, what we said is we skipped 2, and since this path includes the one where we added a 3, so here we're not going to add any 3s, and so we're only allowed to choose 6 and 7. That's going to end up leading to totals of greater than, it's going to lead to either 8 or 9. Those are both greater than our target value. So here, we're not allowed to add any 2s because that's what this path was. So we can add a 3, or we can choose to skip 3 and add nothing. So here, since we're skipping 3, so we're only allowed to add 6s or 7. So here we can say, okay, get a 6. This path, we skip 6, so we're not allowed to add any 6s over here. And from over here, we'll say, okay, we can add a 7, which will give us the total 7, right? That's the target that we're looking for, so we did end up finding that. So that's our second solution that we found. Now, since this path is going to lead to combinations that do include a 7, this path cannot include a 7, but you notice how as we are continuing to go down right paths, what we're saying is, okay, we're basically removing
Hey,
we can choose from, right? We're popping 2 initially over here. Then when we go down here, we're not allowing ourselves to choose 3. Over here, we can't choose 6. Then when we finally go down all the way over here, we're not even allowed to choose 7. So therefore, we have no choices left. So this is also going to be a base case because we ran out of elements. And the way we're going to be tracking which elements we can choose from is we're going to have a pointer. Let's call it I. And so initially it's going to be here, which means we can choose any of these elements. As we pop an element like this one, we'd end up taking our I pointer and shifting it over here, which tells us, okay, we can only choose these elements now. So that's the main idea. This is going to be a recursion tree. Each recursion step, we can make 2 decisions, and it's pretty easy to code up once you can kind of understand this logic. Let me show you how to do that. By the way, the time complexity of this, you can see that our decision tree, we're making two decisions each time. So it's going to be 2 to the power. What's the height of our decision tree going to be? Well, each value in this is going to be positive. It's going to be at least 1. So the height of the decision tree can be at most whatever the target value we're trying to make is. So t, so 2 to the power of t, where t is the target value. That's going to be the big O and big O time complexity of this problem. So we are going to do this recursively, but let's have our result variable, which is basically going to be global for the scope of this problem, because I'm going to define a depth for search function inside of our outer function. So a few variables we're going to pass into here. We do want to maintain which of the candidates we're still allowed to choose. So like I said, we're going to have a pointer I that's going to determine that. We're also going to have a current variable. We're only going to have a single occurrence of this. It's just going to be a list that tells us what values we have added so far to the current combination. For example, like we could have 2, we could have 2, 2, or 2, 3, etc., etc. And for the values in our current combination, we do want to have a total. So we want to be maintaining what's the total sum of those, because if it ever reaches our target sum, then we know we have found a solution. If we ever go over our target sum, that means we've reached the base case and we can't continue anymore. So in our DFS function, let's go ahead and define those base cases. We know the base case is the total ever instead of reaching target. That means we found the result. So what we're going to do is result.append. We want to append the actual combination, so we're going to append current. And since we're only maintaining a single variable list for current, we don't want to actually append current itself. We want to create a copy of it, because we're going to continue to use this current variable when we're doing the other combinations recursively. So we don't, because then we're going to be modifying it. So we just want to create a single copy before we actually add it to the result. And after we're done with that, we don't want to continue the rest of this function, so we're just going to go ahead and break out of it by returning. So that's the base case where we succeed. What's the base cases if we end up being impossible to find a combination? Well, one is going to be if I is out of bounds, meaning we can't choose any more candidates. So if I is greater than or equal to candidates, or our total ended up going over the target that we're trying to reach, that's a base case where we have to return immediately because we cannot find a combination. Now for the actual recursive step, remember we have two decisions to make. We can choose to include the value at candidates of I. Right, we can choose to include this value. So what are we going to do if we're including this value? Well, first of all, we're going to take our current values that are in our combination. We're going to take that candidate and go ahead and append it to our current combination, right? We're going to do that before we end up actually calling our DFS function. So we're going to call DFS, and what are we going to pass in? Well, we're including this candidate so we can potentially continue to include it, right? So what we're going to say for our index I that we're passing is I stays the same, right? We're not restricting which candidates we're allowed to choose from just yet. So I stays the same. We pass in current because we just updated it right now, so we can go ahead and pass it in. And the total did end up changing, so we took our current total and added this candidate to it, right? So we can go ahead and pass in total plus candidates of I. So let me delete this line because we're not doing anything with it. Pass in total plus candidates of this candidate to it, right? So we can go ahead and pass in total plus candidates of I. So let me delete this line because we're not. Doing anything with it. But yeah, so this is going to be that first decision where we do include the candidate. Now the next decision is going to be where we can't include it, but after we call this function, we want to clean up a little bit. We ended up adding this value to our current candidates, our current combination, so we want to go ahead and pop that before we go down the other decision. And so once we pop that, we can go down to the other decision. That's if we're not ever going to include this candidate. So for the index, we're going to pass in I plus 1, indicating that we can't include any occurrences of I. And for current, we just go ahead and pass in our current combination. And total is going to stay the same because we didn't end up adding any value to it, right? We left our current combination as the same as it was before when we actually called this function. And once that's done, we've basically made our two decisions, right? Can you see what's going on? Can you see that we called that for search once, and then we called it a second time? So we did create that two branch decision. And after we're done with that, we can go ahead and return. And in this case, we actually don't need to return. So that is the entire DFS function. Last but not least, what we want to do is actually call it out here. So we're going to call it passing in 0 as the beginning index, passing in an empty array as the current combination, and passing in 0 as the current total. And then once that is done, we will have updated our result, which we declared up here, and then we can simply go ahead and return that result. It should contain all of the combinations that end up totaling to the target. So you can see this problem isn't too bad to code. This backtracking approach isn't to the target. So you can see this contain all of the comp here, and then we can simply go ahead and return that result. It should contain all of the combinations that end up totaling. Hey everyone. And for the we can't continue anymore. That means we want to be maintain we and since we're only maintaining a single variable. Hey everyone, welcome back, and let's write some over our target sum. That means we've reached the base case and we can't continue anymore. So in our DFS function, let's go ahead and define those base cases. We know the base case is if total ever ends up in a combination. The rest of this function, so base will define a combination. So if I is greater than or equal to candidates, or our total ended up going over the target. That we're trying patience to include this value. So what are we going to do if we're going to take that candidate our current combination, right? The, we're going to do that before we end up actually calling our DFS function. So we're going to call DFS, and what are we going to pass in? Well, we're going to current and so we can go ahead and pass in total. But yeah, so this decision is that we ended up adding this value to our current candidates, our current combination. So we want to go ahead and pop that before we go down the other decision. And so once we pop that, we can go down the other decision. And that's if we're